I will start here with the tasking webinar calendar. So today is 15th of October. We will cover the first session of the webinar series. And for this webinar series, the part one will cover the Infineon TriCore architecture. So we'll have here in the session a clear and complete overview about the different components inside the architecture and how to configure different components and the different aspects of different modules. The second part will be tomorrow on 16th of October, and this will cover more the tool set that you could use for TriCore and building a multi-core based safety critical applications on the TriCore. So please mark your calendar as well for tomorrow, 16th. On 10 o'clock, we will start the second part of the session. And then in November and December, we will have more webinars where it cover in the 21st of November, we will cover the qualification aspect of the tool chain and qualifying the tool chain according to ISO 26262 and not only ISO 26262 for other standards as well. And on December, on 19th of December, we will have here some specific tools that solve a very critical problems for our customers when it comes to performance and when it comes to safety as well. So at least this is the calendar. Please make sure that to mark your calendar as well according to this calendar. I will jump quickly to the agenda. So in today's session, we will cover the TriCore architecture part, and in this TriCore architecture part, we will see the different data types that are supported by the architecture, the data alignments, the memory models, the different addressing modes, what are the fast addressing modes, what are the modes that cost me a bit of extra coding and extra performance, and what will happen, for example, if the addressing mode is not supported by the TriCore architecture. And we will see a conceptual view about the tasks. So what are the tasks and what are the context switching between the tasks. And we will see the interrupts, how the interrupts works, and the traps. That's a bit similar to the interrupts, but it has special cases when it comes to traps. The Infineon TriCore is very famous when it comes to as well to safety critical applications. That's why it offer a very complete schematic when it comes to the protection, the memory protection system. This is what we will see as well in this webinar. We will see how the memory management unit works and the floating processing unit works as well. So this is the content of the first part of the session. The second part, it will be tomorrow on 16th. We will see from the compiler point of view the different optimization levels. So if I want to optimize aggressively, or if I want to optimize a little bit, or if I don't want to optimize at all for certain reason. So we will see here the optimization levels, the optimization pragmas, and how could you use it, and the front-end optimizations and back-end optimization algorithms. So this will be covered tomorrow. Tomorrow as well, we will cover a complete example about how to building a multi-core based application on the TriCore architecture from early beginning, from the design phase till the end. So this will provide a clear overview about the essential knowledge that you need to have in order to build a multi-core safety critical application on TriCore. And then I will give you in the second session as well a bit about sneak peeks about the next seminar. So what you are going to see in the upcoming seminars. So at least you have a bit of sneak peeks. If it's interesting for you, you could definitely participate in the next seminars. Okay, so this is the agenda. I will give first a bit about overview about the tasking portfolio, what we are having in our portfolio. So definitely we have the tasking compiler. So the tasking compiler, it is for TriCore definitely, and for other architectures as well. The compiler itself, it's ASPICE level 2 compliance, and we had got a certificate from TÜV, I think few weeks ago, that state as well that the compiler is useful for safety critical applications up to ASIL D with TCL or tool confidence level 3, which is the highest level when it comes to the safety. We have, from the optimization point of view, we have the embedded profiler. So as embedded profiler, it's a desktop tool that's specifically aware about the Aurix architecture. So it shows you in a runtime what are the bottlenecks into your software are, and it doesn't shows only the problems, but it shows as well how could you fix such problems. So it gives you suggestions what is the problem is, and what the developers could do in order to solve this optimization problems. We have as well an LabPack performance library. So the LabPack performance library, it's a C-based library. It's as well optimized specifically for the Aurix architecture. So the best use case for this library may be when you receive a 2D data that comes, for example, from a camera, and you want to process this data. So and you need to at the same time comply to your real-time requirements in terms of timing. So this will fit in this context. For example, we're having a price competitive debugging solution as well for TriCore. And from the safety side, we have the safety checker, which is a static analysis tool that achieves this principle that's called freedom from interference. And this freedom from interference concept is already mentioned in ISO 26262 with this exact text, freedom from interference. And freedom from interference means if you have, for example, different software components and you want to make sure that the higher critical software component is protected from less ASIL based software components. How could you make sure this freedom from interference between these software components is already achieved? There are definitely different solutions, but to achieve it in an automated way for our customers, this is basically the motive for us that we develop the safety checker for this purpose. From the safety point of view as well, we have the compiler qualification kit. So the compiler qualification kit, it provides you the evidences that the tool chain is suitable for your safety critical environment, and it gives you as well the evidences accordingly. So to summarize this, we have the compiler, we have optimization tools, we have a debugging solution, and we have safety related products. So this is a bit about what we are having in our portfolio. We'll jump quickly to the session of today. So here, in order to understand any architecture, you have to look at the first on the ISA, or instruction set architecture. So the instruction set architecture, it gives you a complete overview about what the architecture provides. So here you could find for TriCore, it's a 32-bit architecture, and accordingly, it is provide 4 gigabyte of the address space. So this is the address space that you could use with this architecture. If the code size is important for you, so the architecture provides 16-bit instructions and 32-bit instructions as well. Most of the instructions, they are executed in one cycle, which is really very good in terms of performance. And you will find as well some branch instructions already supported. And from the interrupt point of view, you will find that the architecture itself, it offers a low interrupt latency because as we will see in the presentation, there is a hardware intervention when it comes to context switching between different tasks, and this will definitely provide low latency for your interrupts. There is a kind of dedicated interfaces to application-specific coprocessors. So you will find, for example, GTM or generic timer module, or hardware security module, or the rest of the coprocessors. So all this, there are a dedicated interface for this. The architecture offers something called zero overhead loop, which means the endpoints of the looping, they are defined by the hardware. So there is no need of additional software that need to be applied in order to find out, we already reached to the end of the looping and we need to start again. And such capability is really very appreciated by the, for example, the DSP algorithms, and because it is the heart, the loops, they are the heart of the DSP algorithms actually. There is multiply and accumulate units. So there are two units on the architecture, and the arguments for this is 16 by 16 bit. And you will find some optional components that already existed on the architecture. So optional means it could be on some derivatives, and some other derivatives this components doesn't exist. So you'll find some derivatives have FPU. So FPU stands for floating point unit, and you will find as well the other optional components that's called MMU, or memory management unit. And we will see in detail what are these modules are doing exactly, and how could you use it for your application in the next slides. The architecture, it provide as well extensive bit handling on the bit level as well. So this is really very good if you are making some or referring to some logic based on the bits and you want to process these bits. So the architecture, it offers this bit handling capabilities. There is something called SIMD, or single instruction multiple data instruction. So this is an instruction that takes maybe two operands, and each operand is 16-bit, or four operand and each operand is 4-bit. And it supports as well the flexible interrupts. So flexible interrupts means if you have interrupts, you could prioritize the interrupts. You could as well have a different, on the same interrupt, you could change the priority of the interrupt on a real time, and you could as well have one interrupt that has maybe different parts of it, and for every part, you are going to associate a different criticality. So as architecture, it offers a flexible interrupt prioritization scheme. And you will find as well addressing on the byte and the bits as well. And the data and the CPU registers, they will be located in the memory based on the little endian. So we will see what does it mean in details in the next slides. And definitely memory protection is supported with the different methods, and co-processor support is exist, and the debug support as well. And the debug support, for example, it's really very it's unintrusive. So that means if you want to have the debugging stream, this will not have an impact on your real-time performance of your application, because the debugging, it is non-intrusive debugging. So at least this is here the instruction set architecture for the Aurix. And what we are going to do in this session, we are going to discuss the different aspects of this instruction set architecture. So let's have a look here quickly on the architectural registers. So on the architectural registers, you will find there is address registers, there are data registers, and there are system registers. So here, this is the 32-bit general purpose registers. This is, if you combine the 16 address registers with the 16 data registers, you will end up with the 32 general purpose address registers. And we have as well the BC register. So this BC stands for program counter, and this program counter, it refers to the current instructions that needs to be executed by the CPU, and you will find it here under this system part. And you will find extra additional two 32-bit registers that contain the status flags, for example, and the previous context and the protection information. And all this existed in these two registers, so PSW, or processor status word, and previous context switch. So these are the two registers that contain this information for you. It's really very important to note that the previous context switching register and the password status word register, processor status word register, and the program counter, they are part of something called task context. And what is a task context? We will see it in a short, but in a brief. Any task, it needs, or it has a certain informations. And when there is a task context switching between these tasks, this information need to be restored or loaded in order to let the processor to continue executing these tasks. And these three registers, they are part as well of the context for the task. So let's dig deeper inside this address space and the data registers. So you will find for the data, you have the 16 registers. Every register is 32-bit and start with D0 till D15. And for the address registers, you will find as well 16 registers. Every register is 32-bit register, starting from A0 till A15. And you will find as well, there are some registers that has dual functionalities or some special functionalities. For example, D15 here, it is worked as implicit data. A15 or A0 at the beginning, it works as well as a stack pointer. So it refers to the stack, and A11 address register, it holds the returning address. So for example, if I jump to a certain interrupt, so I need to save this returning address in order to know where I should start after this interrupt ends. And this A11, it holds the returning address in this example. And I have as well the A15 that works as implicit address. And A0, A1, and A8, and A9. So here, A0, A1, and A8, and A9, they are belongs to the system global registers, and they are really not included in either the upper context or the lower context of any context. So for the context, any context is divided into two parts, lower context and upper context. And for these registers, A0, A1, A8, and A9, they doesn't belong to any of this context, and they are using by the operating system to reduce a system overhead. So to sum it up, we have core registers. They are divided into two parts, general purpose registers and core special function registers. So the general purpose registers, this is what we already saw. These are the 32-bit, the 32-bit registers, and this is represented in the lower and upper part of the context. And for the core special function registers, you will find some registers related to the system. So it's system registers like processor status word and program counter and previous context switching, and some registers related to stack management, some configuration, system configuration registers and CPU ID registers, some registers related to traps, some registers related to context management, memory protection, and memory management, and some registers related to the debugging as well, and some registers here related to the floating point, if the floating point unit already existed. And you will find as well some special function registers that are related to a specific core. So this is a complete overview about the core registers, the different cores, the different registers that existed on the TriCore. Okay, so as we agreed, we have here a lower context and upper context. This together represents something called context. So for the lower context, you will find here the lower context exists or consists of the address register A2 till A7. So this is A2 to A7 inside this address registers. And from the data part, you will find the lower context. For the lower context, it starts with D0 till T7. So D0 till D7. And this is information is represented in the lower context. So this are here like highlighted in green, they are the lower context. And for the upper context contains from A10 till A15, this part, and from the data registers, it contains from D8 till D15. And please note that as we agreed, so A0 and A1, A8 and A9, they really doesn't belong to any of the lower context or the upper context. Yeah, so as we agreed, it's used by the operating system to reduce the system overhead. This is the idea behind these registers. Okay, so from the data type, so we have here the architecture support different data types. So it support Boolean. So here's a presentation of the data type. So for example, the Boolean, it's only one bit that contain a value yes or no, or true or false. We have bit string, bytes, signed fraction, address, signed and unsigned integers, and the floating point, a single precision floating point, and it's compliant according to IEEE 754. So this is a representation of the floating point. Here you will find the floating point. It contains of two parts, so the fraction part and the exponent part, and you will find at the end this S, and S refers to this binary point. So this is represented if this floating point, for example, is a positive value or a negative value. I believe 0, it means positive, and 1, it means negative. And if you want to use this floating point, you have two options. So you could use if the floating processing unit already existed on the hardware, so you could use it to run specific instructions for this floating point calculations, or you could use software calls to the libraries. So these are the two methods if you want to use this floating point. From the data alignment, the alignment means where, on which levels or on which address should the data and the addresses be aligned. So it's different if you align an address or an data. So this is the guidance that comes from Infineon in this regard. So for the data registers, regardless of the access size, I would say it's for the data registers, they are aligned on a half word, because as we agreed, it's 32-bit architecture. So one word means it's a 32 bit or 4 bytes. So here the alignment is on half word. For the addresses, the alignment will be on a full word. And you will find some special cases. For example, ST instruction, it will be require alignment on a byte level, and swap instruction or load most, it requires that the alignment will be on a 4 byte alignment. And for the context switching, so the context load and store, so the access size in this case, it's 16, this 16 times registers that we saw in the previous slides, and it requires alignment on the 64 byte. So this is here the guidance when it comes to the alignment as well. In terms of indianity and what indianity for the data is, so indianity means how this data represented in the memory, starting from low up or from up going down. So for example, if I have a byte, so this is the memory here, and if I have byte, so the byte will be laid like in one box, I would say, like byte 0. Or if I have word, which is 4 byte, so it will be laid inside the memory like this, byte as the first byte here and the last byte there. So from the lower significant byte, it will be here, and the most significant byte, it will be there. And if you have, for example, half word, so again, the lower significant byte, it will be there, and the highest significant byte, it will be there. And for the double word, which is here 8 words, again, it will start with byte 16, 17 till 32. So this is how to fill the memory with such data. This is the indianity of the different data types. Yeah, let's speak a bit about the memory hierarchy. So here you can find the hierarchy of the memory system that exists on the TriCore. Don't worry, it doesn't really look very complex as it looks from the first insight. So here we have the TriCore CPU. So this is the central processing unit, and we have here the BMUs, or the BMU flashes. So these are the flash memories. And the challenge here is, how could you compensate the speed difference between the CPU and the BMU flashes? Because definitely the CPU, it's way faster than the BMU flashes. And in order to compensate this speed difference, you will find that the architecture bought something called an instruction cache here, and this is 16 kilobyte instruction cache. And here it contains the instructions to be executed, and from the data section, the instruction the architecture put 16 kilobyte data cache as well for the data, and this provide a faster access or fetching of the data and the instructions from this memory. And you will find as well, if you need deterministic behavior, the architecture provides 32 kilobytes program scratchpad RAM. So this is for the instructions, and 128 kilobyte for the DSPR or the data scratchpad RAM. And yeah, this is how it looks like. So you have the CPU, they have the BMU flashes, you have BMI, program memory interface, and data memory interface. And you will have as well the LMU. So LMU stands for local memory unit. So this is a shared memory between the different cores. And you will have external RAM and external flash as well. So this is here the complete hierarchy of the memory. So the CPU and the BMU flashes, they are connected to a different clocks, definitely, but both clocks, they are derived from the BLL output. So BLL stands for phase locked loop, and this basically from where the clock source comes, and we use different dividers in order to get the proper requested clock. But if the clock speed doesn't exceed 150 megahertz, so that means you could connect the TriCore with the BMUs with no problem. As I mentioned here, for the caches, we have the instruction cache and we have the data cache. And for your application, it really depends on your requirements. So your whole application could be cached, or part of your application could be cached, or you could not use the cache at all. So it really up to you to use it. So you have the CPU, you have the instruction cache and the data cache, which is a fast access. For deterministic access, you have BSPR and DSPR, and then comes the role of the BMU and BMU0 and BMU1 flashes, and then the LMU, and then the external flashes. So this is the sequence from the fastest memory to the slowest memory. Okay, so let's cover one memory at a time. So let's speak here about the instruction cache. So the code that's located in the BMU0 or BMU1 or LMU even, or external RAM or external flash, this could be cacheable. And in order to make such code cacheable inside this instruction cache, you need to fulfill some conditions. So first, you have to locate the code section or locate your code inside this 0x8 segment. Sorry, if there is not LMU existed. And what does 0x8 segment means? So a quick idea about the memory. So the memory, it consists of 16 memory segment. Every segment is 256 megabytes. So you have to locate your code inside this memory segment, and in case there is no LMU, and if case there is LMU, you have to locate your code in 0x9 segment. So this is a segment above the other segment, and you have to enable the instruction cache. So by default, it's enabled, but it's not configured. So please take care. You have to enable the instruction cache, and you have to configure as well as the instruction cache bypass to be deactivated. So once all these conditions are fulfilled, then your code that will be existed in these areas will be cached. And the code that exists in the BMU0 or BMU1 flashes, or external RAM or external flash, or the LMU, it will not be it will not be cached if it's saved inside this 0xa segment or 0xb segment, based on there is LMU supported or not. And again, you have to here make the instruction cache bypass is active. So in this case, your code will not be saved, in the instruction cache. And yeah, it depends basically here on your requirements. So if you want your code to be cacheable, so you have to put it in the segment. If you don't want your code to be cacheable and you want a deterministic behavior, so you have to put your code on this segments. And yeah, please take care that there is something called BMA0 register that is controlled partially the cacheability of some segments. So please take care to have a look on this when you configure the instruction cache. And the code that could be saved inside this instruction cache, it could be something that comes from BMU program flash, or BMU0 BROM, or BMU one flash, or the local memory unit as well, or the external memories. So these are the memory segments where the parts of the code could be cached inside this instruction cache. Again, the same story, but here for the data cache. So for the data cache, yeah, it's related more on the data. So you will find as well here the data that's located in the, again, BMU0 or BMU1 flash, or the LMU or external memories. It could be cacheable once it met all these conditions. So for the data, it will be located in 0x8 segment or 0x9 segment, again, based on there is LMU or not. And you have to enable the data cache, and at the same time you have to make the data cache bypass deactivated. So once all this once all these conditions already fulfilled, then the data will be cached inside this data cache. And again, if you want your data not to be cached, so you have to put the data here in 0x8 A segment if there is no LMU, or you have to put your data in 0xP segment if there is LMU existed, and you have to highlight it that the cache bypass is activated. So in this case, the data will not be cached. And again, we have this famous thing, it's called BMA0, that again controls the cacheability of your data. So please have a look on it when you configure the data cache as well. And yeah, what could be cached in principle? So here, the BMU0 flash or data flash, or BMU1 program flash, external memory, and the LMU. All right, so we have here, as we agreed, the TriCore architecture. It's a 32-bit architecture, so you will end up with 4 gigabytes of memory. What's interesting here is not accessing the access to all this memory. It's not provide the same time as it's the same access time for every memory. So it depends on which section of the memory you will find that the accessing for the data or the instruction in this segment is fast or not. So you will find here something called absolute addressing. And absolute addressing, it is basically available for the first 16 kilobyte of every segment. So we agreed we have 16 segments. So for the first 16 kilobyte of every segment, this absolute addressing is available. And the second addressing mode here is base plus long offset. So base plus long offset, as the name tells it, you have a base address and you add additional offset on this, and then you jump to a certain place in the memory. And here it uses this global base registers. You remember that doesn't belong to the lower context, to the upper context. That is A0, A1, A8, and A9 registers. And this is provide efficient access for the second 64 kilobyte of every segment. So here, this is the fastest way to access the data and the instruction. And then here, this is the second fastest way to access the data and the instructions. And yeah, definitely you have to configure the tool chain settings in order to use the segments properly. So you have to configure definitely the compiler part and the linker part, and this section here, it will be covered in the second part of the webinar. So for the short addressing here, you have the near addressing, and this is, let's assume this is a segment, and the first 16 kilobyte of the segment you could access with this near, it's called near segment, and you could access it with this short addressing. So in order to make this, you have to, so the address basically, it contains of yeah, 16 it contains 16 kilobytes. And for the memory here, you will find these are the memories that you could use in order to use a near addressing mode. So BMU0 program flash, this is suitable for this near segment. You have DSPRs as well as the LMUs, and this addressing mode, it works for the constants and for the variables if they are initialized or not. And here you could find the compiler default sections. So the compiler you will find inside something called map files that's generated by the compiler. This is the section name for such data and for such memories. And yeah, as I mentioned, this is really very fast accessing mode, and it is a kind of a pity if you want to save some structures here that they are not accessed with this near addressing. So for example, CSA or context save area or the stacks. So this is a kind of memory structures, and this memory structures, they are not accessible through this near addressing. So it really doesn't make sense to save such stuff inside this memory, and it makes more sense to save such data types there. And from the compiler type, in order to enable this near addressing, you have different possibilities. So from the compiler option, you could use the compiler option that's called default near size, and this represents a threshold for your data. So if the data exceeded this threshold, it will be saved away from this near segment. And if, as long as the data size is below this size, by default, it's 8 bytes. So as long as this below this default near size, it will be saved here inside this near section. So this is the first option, to use the compiler option in order to force the linker to locate the data inside this memory part. Or the second option here is to use the pragma. So the pragma here you could use in order to as well influence the compiler to place the data here. And the third option is to use the memory qualifier. And for the memory qualifier, this is it's called __ near. So you have to put in front of the data element that you already declared this keyword, and the linker will automatically place this data inside this near segment. So these are the three available options here. And yeah, so let's see what are the differences between these options. So the first one, it's called default near size. This is applicable for your whole application. So if you want to apply a fixed rule for your whole project, you could use this compiler option. For a certain code modules, if you want to apply it only for certain code modules, you could use this pragma section. And for if you want to declare only a single data object and you want to put it here inside this near segment only on the scope of this data object, you could use this memory qualifier. So these are the differences between these three possibilities in order to force the data to be saved here inside this near segment. All right, so let's see the second addressing mode that's called base plus offset. So inside this second option that's called base plus offset, the address, in order to be formulated, it uses the global base registers A0 or A1 or A8 or A9. So for A0 and A1, so these are the proper memories that you could access with this address registers. And for A0, it's specifically for constants. So this address register A0, it will be used to reference constants. And for A1, these are for the variables, if they are initialized or not. And again, this is the compiler sections that are generated from the linker at the end inside the map file. We will cover this, by the way, in the second section or the second part of the webinar tomorrow. For the A8 and A9 addressing mode, these are again the memories that are supported to use this addressing mode, and these are the data types that could be used. So the constants and the variables, if they are initialized or not, and again, the generated compiler sections. So how could you configure this from the compiler point of view? So for the A0 and A1, you have kind of the same possibilities like we saw previously inside the near addressing. So you will find here this default A0 size. So if you notice, previously it was default near size. In this time, it's called default A0 size. So you could use this compiler option. Or for A1, you could use this compiler option default A1 size. And you could as well use the pragmas in this case. So you could use the pragma default A0 size. And you could use the second one for A1 address register that pragma called default A1 size. Or you could use for single objects underscore underscore A0 or underscore underscore A1. So this is as well only for single objects. And again, there's a compiler option here. This is available for your whole project. The pragmas are applicable for only a certain modules inside your project. And for single objects, you could use this memory qualifiers. And from A8 and A9, you could have the possibility to use only memory qualifiers. And in this case, you could use underscore A8 and underscore A9 in front of your data objects in order to place the data inside a memory segment that are accessible with this address registers. And by the way, you could notice as well here the difference between the generated code if you use the base plus long addressing against if you put your data in a far addressing, which is not a near data, not base plus address, it will be inside this far related memory. So you could see here the generated assembly for this base plus long offset. It's more faster and more optimized as well. It is the same as well for the near addressing. So this is a generated assembly code for the near addressing against if you place the data inside a far memory. So this you will need definitely more effort in order to fetch the data. Okay, so to sum it up, so we have program scratchpad RAM, instruction cache, that scratchpad RAM, and data cache. And then you will have BMU0 flash, BMU1 flash, and you will have local memory units and external memories. And this is a direction from faster memory to a lower memory. And you will find here the starting addresses for every memory type if you want to make this data non-cacheable, or if you want to make the segments as well cacheable. And here some remarks: if you for example want kind of deterministic behavior of your source of your code, so it makes sense to put it here in the program scratchpad RAM, like operating system or DSP algorithms, where it's really very critical and they need deterministic behavior of the code. So to put it here inside this program scratchpad RAM. For the instruction cache or for the data cache, yeah, if you want a faster access for your data or for your code, so it makes more sense to put it inside this instruction cache or the data cache. All right, so to sum it up again, you will have some typical use case, like something like this. So you will have here, this is the BMU0 flash. You will find this is a data scratchpad RAM or program scratchpad RAM and the local memory unit and peripheral mapped sections. So you'll find in every part here the first 16 kilobytes. This is the near addressing of the memory. And you will find here this A1 memory and A0 memory, and then A8 memory and A9 memory. This is the second fastest mode, and then the far memory where one need more time in order to fetch the data or fetch the instructions. Yeah, for example here for the preferences as well, you will find a near preferences and far preferences. So it depends on your requirements. If you want to access a certain peripheral on regular than others, so it really makes sense to declare it as a near. If you want, if you don't access this peripheral regularly, so it makes sense to declare it as a far. All right, so this is for TriCore 1.3. You will find here this is the memory segment. So as we agree, we have a segment from 16 segment. It starts with 0 and then ends with F. So it's 16 segments. And for every segment, it has a dedicated definition. So from 0H to 7H, so the lowest part of the address space, it is related to the virtual address space. It depends, it's implementation dependent if there is a memory management unit or not. And then these two segments, they are related to the cacheable memory, and then A and B segments, they are related to non-cacheable memory, and then C, it is related to a cacheable memory again, and you will find then starting from D, segment D, it's scratchpad RAM, and then for peripherals is the segment E and F. So, and as we agreed, the fastest addressing mode, it's near addressing, and this is for the first 16 kilobyte. So inside this address space, you could fetch any of the segments with this fastest mode of the using the 16 kilobyte section of every segment. And yeah, this is here a new slide. So if you notice the difference between TriCore 1.3 and 1.3.1, so this is the upgrade of the TriCore 1.3, you will find basically the difference is here inside the scratchpad RAM. So for scratchpad RAM for 1.3, the scratchpad RAM, it is only D segment, and for 1.3.1, the scratchpad RAM, it is for segment C and D. And this represents the differences between the 1.3 and 1.3.1. So segment D for 1.3, the segment D contains the scratchpad RAM, and the scratchpad RAM could be one thing of two. So it's either DSPR or data scratchpad RAM, or BSPR or program scratchpad RAM. And for TriCore 1.3.1, you will find that segment C and D, so it contains the scratchpad RAM, so data scratchpad RAM again, and program scratchpad RAM. So these are the differences between 1.3 and 1.3.1. Okay, so we saw here, these are the addressing modes. We cover a little bit of them. So they are, I believe, 7, 1, 2, 3, 4, 5, 6, 7. So there are 7 addressing modes. Some addressing modes doesn't need any registers because it only use a part of the instruction to access the memory. And some other addressing modes, they need only one register, and some other, they need more. And the point here is, I will not go through every single addressing mode, but I already had a detailed appendix inside my presentation. So if you would like, I will share the presentation, and you will find the rest of the addressing modes inside the presentation as well. And by the way, there are more addressing modes. It's not supported by the TriCore, but it doesn't mean that you cannot use them. So you could definitely use them using some combination of different instructions. So you could end up with a synthesized addressing mode based on this base addressing modes. All right, so I will cover here only this absolute addressing. So for this absolute addressing, this is how to form the address, the 32-bit address out of your instruction. So this is an instruction. So you will find here I use this 18-bit. So the first I will use the first 14-bit. It will I will use them exactly like they are, and then put this 14, the second 14-bit as zeros, and then put the last 4 bits of this 18-bit in the end of the address register, and then yes, I have the complete address for the addressing mode. So I use the 18-bit that comes with the instruction, and you will find here this 4 bits. It is 4 because it is a 16 memory segment, right? And for the 16 memory segments, in order to access all the segments, you need a 4 bit, and this 4 bits provide different combinations in order to fetch whatever segment you want. And again, you could check this appendix D for more addressing modes. All right, so I will cover here a new topic, which is related to tasks and contexts. So for the task, what is a task? So the task itself, it is independent thread of control. So this is the definition of the task, and the state of the task, it is defined by something called context. And this context the processor needs in order to re-enable the execution of a certain task. And the tasks itself, there are two categorizations of a task. There is something called SMTs and ISR. So SMTs, it stands for software managed tasks, and ISRs, they are interrupt service routines. So these are the two different types of tasks. For the SMTs, or software managed tasks, so they are created by the utilities that comes with the operating system. So basically, you could create it with the kernel of the operating system, and they are dispatched using the scheduler that comes as well with the operating system. And for the interrupt service routines, they are dispatched by the hardware. So there is no software utility to run in order to run them. So they happen by the hardware in response to a certain interrupt. And the interrupt service routine is basically a code that needs to be invoked or called based on this reception of the interrupt. And sometimes this SMTs or software managed tasks, they are have a different name that's called user tasks, because usually most of the time they are executed in a user mode. That's why it's called user tasks. And in the TriCore architecture, so you will find basically the RTOS layer. It's really very thin, or very not very big, because there is a hardware intervention when it comes to context switching between the tasks, which is really save from your side really a lot of work and time, because I really used a lot of architectures, and yeah, this is kind of new thing for me, that the hardware could take over and make this context switching between as the tasks. It's something that I found really very interesting from Infineon and from TriCore. All right, so we have here for every task, every task could have its own mode. So there are in the TriCore 3 modes. There is a user 0 mode, user 1 mode, and the supervisor mode. For every mode, the differences are in accessing if this mode have access to certain preferences or not, and they are able to enable the interrupts or not. So for user 0 mode, this is the lowest or the less permission mode, where they don't access any of the preferences, and at the same time they cannot enable or disable the interrupts. Then comes this user 1 mode, where some common unprotected preferences could be accessed, like for example reading some timer, for example, or reading or writing some UART. So such stuff that are really not very critical, it's okay for this mode to be accessed. And in this mode, this may be disabled as the interrupts as well. For the supervisor mode, and from its name, it's supervisor, so you can do everything. So it can read and write certain registers, system registers, and all the preferences, and definitely it could disable the interrupts. And yeah, individual modes here could be selected based on the input-output mode bits that already existed inside processor status word. So please refer to this processor status word if you want to change the input-output mode bits for any of your tasks. Yeah, and as we agreed here, the task context, it contains of the general purpose registers, and the program counter definitely, and these two system registers, previous context switch register and program status word. So these are here represent the task context, and this always the information that's related to a task. So in order to continue executing the task, the processor need to know exactly what is the program counter value, what is the BCXI value, what or the previous context reference, and the processor status word, and the general purpose register values in order to continue executing this task. All right, so for the context switching, we have, as we agreed, a lower context and upper context. So this is here the memory, and this is a kind of overview. What are the contents of the lower context? What are the contexts of content of the upper context? And for the upper context, it consists of A0 till A15 and D8 to D15, and at the same time it contains this processor status word, and at the same time BCXI, or something called link word, and we will know shortly what this link word means. And for the lower context, it contains from A0 to A2 to A7, and from the data register D0 till D7, and A11, which is holding the returning address, and the BCXI again. And here it's called link word. And yeah, for this context, either for the lower context or for the upper context, they are occupying the 16-word block. So in order to save the lower or upper context, you need a 16-word memory space. And this link word, it links, so it links the current context with the next one or the previous one. So it's the representation of the context switching between the tasks. It's it uses something called linked list. So that means if you have one object that's referred to a next one, that's referred to next one, that's referred to next one. So in every object, you need to hold a reference to the next one. And this is here the link word. All right, so as we agreed, the architecture, it uses the linked list of a fixed size. So that means you cannot change the size of this context save area. It's always 16 word. And yeah, the alignment for this as well, it's 16 word boundary. So you have to take care when you align your data. And yeah, for the context save area, it doesn't hold both contexts at the same time. It holds either the lower context or the upper context once. So and as we agreed, it uses link word in order to reference to the other context save areas. And yeah, again, the architecture save and restore the context more quickly than other microprocessors, because this hardware intervention when it comes to the context save area switching. And yeah, it uses as well this wide data bus, and this definitely provide a rapid data fetching between the processor registers and the memory as well. And the context switching happens based on certain events or instructions. So when the context switching happens, you will find a different scenario. So if interrupt or service request happen, a context switching will occur, or if there is a trap happen as well, a context switching will occur as well, or a function call. So if one function called one function called one function called one function, so in this case, for every function call, a context switching will happen as well. All right, so let's focus here on this link word. I will let you remember what is this. So this is a link word for the upper context. This is a link word for the lower context. Let's see what this word basically does. So for the link word, it contains two parts. So the first part is something called offset, and a second part is called something called segment. And in order to form the address here, I will fill everything here with zeros, and then put the offset, and then again zeros, and then at the end I will put the segment in order to get something called EA address, or effective address. And yeah, so you have here 16-bit offset. So that means you could access up to 2 to the power 16 CSAs, or context save area. And the total reusable range in every memory segment for CSA is 4 megabytes. Okay, so here this is how it works. So we have the different context save areas. So context save area 1, context save area 2, 3, 4, 5, 6. So you have here something called free context list. And free context list, this is a linked list representation of the free context areas that you could use. And this free context lists, they are referred by something called processor special function register called FCX. And for the previous context list, so these are the context save areas that you already underused or already used currently by the system, and they are referred by a special function register called BCX, or previous context pointer. And you will find here a third pointer here. It's called LCX. It is a limiter for this free CSAs, but let's forget it at the moment. So let's focus on the FCX and BCX registers. So FCX refer to the top of the linked list to the lists of the CSAs that are available in the system, and for BCX it refers to the top of the linked list for the CSAs that are currently used by the system. All right, and for every address here, as you can see, FCX or BCX or the links to any of the CSAs, you will find a 16-bit offset and a 4-bit segment in order to select the segment and then select the offset for this. This is example in order to illustrate how it works in a better way. So let's assume here we have 3 CSAs, 3 free context save areas that are referred by FCX, and we have here an occupied context save areas A1, CSA1 and CSA2, and they are referred by BCX. And let's assume there is a trap happens, or a function call, or an interrupt happens. What will happen in this case? So definitely I need to write the current status of the task in one CSA. And to write such information, I need one CSA from this free context list. So you will end up from here to there. So I will use this CSA that's called CSA3, and I will put it in this previous context list. And I will let the BCX to refer to the updated context save area, and I will update the context save area that's on top of the list to refer to the previous context save area. So in this case, I injected this CS3. I take it out from this free context list and I injected it inside this previous context list because I use it at the moment. And I updated as well the FCX pointer to refer to CSA4 because this doesn't exist anymore. So I updated the value of the FCX to refer to CSA4, and you will end up with something like this. And again, if I already served the interrupt and I come back, or I already served a function call and I come back, so I need to move the context save area to a free list because I don't use it anymore because the interrupt is already happened. I served it and all is good. So I need to again inject the context save area in that from the previous context list to the free context list, and you will end up with something like this. So I updated the FCX to refer to a newly injected CSA, which is here CSA3, and I will update as well the BCX pointer to refer to the top of the linked list, which is here in this case CS2, and this is what happens. So you will find here BCX refer to CSA2. So this is a representation how a context save area is saved and retrieved from this list, and you will find here these are the steps that I already explained in my presentation. All right, so the interrupt system. So let's have quickly an overview about the interrupt system, how it works. From Infineon, it really offers a powerful and flexible interrupt system. And as a concept of the interrupt system, it's based on something called programmable service request nodes. We will see this shortly in the next slide. And for the service request, the service request is defined as one of two things. So this could be interrupt request or DMA request. DMA stands for direct memory access. And this one of two, they represent the service request. And the service request may come from on-chip peripheral, external hardware, or software. So for example, on-chip peripheral, you could receive an interrupt from watchdog timer, or external hardware. If you have external watchdog timer, so you could receive an interrupt from this external watchdog timer. or you could even generate a service request from your software. And what I really found interesting about the architecture as well is it really doesn't take too much time to load the vectors inside the code memory, because traditionally, in order to load this program status word, so you need to jump to the vector table that's already saved in other microcontrollers in the data memory, which is something that takes too much time. But inside the TriCore architecture, I jump directly to the vector table that's already saved inside the code memory, and this will definitely help you when it comes to the interrupt latency. So the latency will be less in this case. Okay, so what I really found interesting as well about the architecture is you could have one CPU that could serve your interrupt, or you could have additional units that could handle the interrupts that you receive. So if you have a second CPU, so you could use a second CPU to serve an interrupt, or if you have a DMA unit, you could use a DMA unit to handle the interrupts, or even you could have some coprocessor like PCB or peripheral control processor to handle your interrupts. So you have different options that are available in front of you, and you need to select any of these interrupt serving modules to serve your interrupts, or the service provider. Okay, so the service requests or the interrupts could be prioritized, and accordingly, you will end up sometimes with the nested interrupts. So, and accordingly, you have some rules. So, for example, if a service request or the interrupt has a higher priority than what's serving at the moment, so it will interrupt the current serving interrupt, and it will take the CPU and let its interrupt to be served. The interrupt on the same level of the priority, they doesn't interrupt each other, and you will have something called here ITU, and this ITU, it is something called interrupt control unit. So it's a unit that's responsible for arbitration on the bus. So if you have two or more interrupts then that need to be served at the same time, so the interrupt control unit is the entity that define who will take the CPU and be served at the first based on the priority of the interrupt. All right, so all service requests, they are assigned something called priority number. So you will end up with something called SRPNs, or service request priority number. And the maximum numbers of the interrupt sources, they are 255, and the programmable options, they are ranging from one priority level with 255 sources up to 255 priority levels with even one source each. And you will find here the interrupt system picture. So this is the interrupt, how the interrupt looks like. So you will find at the beginning of the left, you will find something called service requestors. So they from where the service request comes or the interrupt comes, and you will find here then something called service request nodes, or SRNs. So SRNs, it contains something called service request control register, and it has the required logic in order to let the service requests to communicate on the arbitration bus. And this is the arbitration bus here. So you will have here this CPU arbitration bus. And again, if you want to use a second CPU or a BCB coprocessor or a DMA unit in order to serve the interrupts, we will have definitely another arbitration bus in this case. And you will have the interrupt control unit. So the interrupt control unit, it handles the arbitration on the bus that comes the requests that comes from the requests from the service requesters, and yeah, it communicates as well with the interrupt service provider. So this is in this case the CPU to handle the interrupts. So it communicates with the CPU, and at the same time it gives priority to the service requests that are raised based on the priority. So this is here how the interrupt system works. All right, so let's have a quickly look at what will happen when we enter the interrupt service routine. So what will happen if I jump to interrupt service routine? Before I go through the data sheet, to be honest, I would answer you, okay, if interrupt service routine happens, I will jump here to the interrupt vector table where I could fetch the first instruction to be executed by the interrupt service routine, right? But figure out that the architecture, it does a lot of stuff before jumping to the interrupt vector table and execute the interrupt service routine. So first, the upper context will be saved, and the A11 register is updated based on the current VC or the program counter. So it will hold the returning address in this case, and the processor, it will check if there is the interrupt stack is used or not based on this processor status what interrupt stack. If it's 0, okay, so I could use this A10 address register to use the stack pointer, and in this case I will set it to point to the interrupt stack pointer, and at the end I will the processor will put this processor status word in interrupt stack to 1 in order to indicate okay, so this is already used with this interrupt, and the input output mode is set to supervisor mode, so that means all permissions are allowed, and the memory protection is enabled. The call depth counter is cleared, so we'll start counting from the beginning, and the limiter for this counter will be 64. And the write permissions to the global registers here, it will be disabled, so please take care. If you want to handle the instruction, if you want to handle the interrupt service routine, please make sure that you don't write to any of this because you cannot. The interrupt system is globally disabled, and this will happen by putting this interrupt enabled bit inside this ICR register to 0, and the old value will be saved inside this previous context, and the current CPU priority number will be saved inside the previous context again, and the pending priority, it will be set as a current priority for the CPU. And after all these steps happen, I will end up with fetching the instructions from the vector table. So this is how it works. All right, so let's see what will happen if I exit the interrupt service routine. So if I exit the interrupt service routine, first, I have to restore, or the hardware will restore for me, which is appreciated by the hardware. It will restore the upper context, and this previous CPU number, it will be written to the current CPU priority number, and the interrupt enable will be restored again, and this is what will happen when I exit the interrupt service routine. Okay, so from the interrupt vector table, so in order to fetch the first instruction from any of the interrupt service routines. So first, this is here the interrupt vector table. So it contains of different code blocks. And to fetch the interrupt service routine address, I use this something called BIV register, or I think it's called base interrupt vector, maybe. I think it's base interrupt vector register. So it point to the base of the interrupt vector table, and I use the priority number combined with this base interrupt vector base interrupt vector value in order to reach to the proper interrupt service routine. So I will shift the priority interrupt priority number with this values, and then or the value with the bits from 5 to 12 from this base interrupt vector, and then I will end up with a certain address. And please note that because I make here ORing, it makes sense that I put all the values here to zeros inside this base interrupt vector register. And please note as well that this is here 0 always. So the first bit of every base interrupt vector, it's 0, which means the interrupt service routines, they are aligned, the alignment based on even byte alignment, because here it's always 0. All right, so good to mention as well that the base interrupt vector address, so this is configurable. So that means you could write this base interrupt vector table during the initialization of your of your code. So by default, it's always 0, but you could try write this base interrupt vector value using MTCR instruction. So if you are interested to have, for example, 2 or more interrupt vectors and you want to switch between these interrupt vectors, so you could change the value of the base interrupt vector and you will end up with lots of interrupt vectors as you wish. All right, so let's see here the interrupt priority groups. Grouping, you could group certain interrupts based on your interest, and grouping, once you group a certain interrupts, so that means you one of these interrupts can't interrupt other interrupt from the same group. So for example, if interrupt 15 happens and if interrupt 16 happen, so that means interrupt 16 cannot take the lead and then interrupt the interrupt number 15, right? So because they are belong to the same group. And when the CPU start the servicing of the interrupt, as we agreed, the interrupt will be disabled and it will be enabled again once you could enable it definitely from the software, or you could enable it as well from RFE instruction. So RFE stands for return from exception instruction. So this will enable the interrupt again with this IE bit inside this ICE register. All right, so let's consider this scenario. So for example, I have here priority group number 1 and priority group number 2. For priority group number 1, I have 2 interrupts inside it, 11 and 12 interrupts. And I have here inside the second group, which is group number 2. So I have 14, 15, 16, 17. So this is represents the second interrupt. And once one interrupt happen from here from priority number 1, so let's say interrupt number 11. Okay, so the CPU will be updated. The CPU priority number will be updated with 11, right? And when one interrupt that comes from this priority group happens, so it will replace this interrupt. It will definitely interrupt this interrupt, and it will take the lead and take the CPU because it has a higher priority number than what is currently existing on the CPU, and it will execute. So this is here as a point. You could grouping different groups, and it really doesn't make sense as well to assign a certain priority number to a certain interrupt that is have a value of 255, because if you assign this value to a certain interrupt, so that means the CPU will have the CPU priority number of 255, and this is the highest one. So any interrupt that comes after that, it will not be executed because it has a priority number less than 255. So putting the current CPU priority number to 255, it has the same effect like disabling the interrupt. All right, so this is here a use case that's related to the interrupt as well. So if I have one interrupt, and this one interrupt could be divided in a different pieces. So the first part of the interrupt, let's say it has a very high criticality, but the second part of the interrupt service routine, it's not really very critical. So something like this you could do with the TriCore architecture, because first you have to assign this a very high priority to the interrupt service routine. So once it's happens, it will have really a very high priority. And once the first section of the interrupt already executed based on this high priority, you could lower the priority and then set this bit again that's called interrupt request bit again. And then this interrupt goes back to the CPU, and the arbitration happens for the same interrupt, but with the newly updated priority. And something like this could be doable based because you have a full control over the interrupt request and the priority. So you could have a full flexibility if you have different sections of the interrupt that has different priorities. All right, so sometimes as well, the priorities that's assigned to the interrupt, it's could be changed with the time according to your system requirements. So for example, at this initial phase, the priority of the interrupt will be high interrupt, and then based on some evidence, some event or some action, the priority of this interrupt will be lowered against other priorities. And something like this as well is doable with by controlling this special request priority number. So this priority number, once you update it, so you could have a full flexibility of your interrupt priority compared to the rest of the priorities. Okay, so there is something called software posted interrupt as well. So the software posted interrupt, it's basically a hardware interrupt, but the point here is there is this bit that's called service request that's already sitting using source software, and it's not updated with the hardware. So this is basically the difference between software posted interrupt and a real hardware interrupt. And because this could be considered as a real hardware interrupt, so once this interrupt happens, you cannot distinguish basically between if it's a software posted interrupt or a hardware posted interrupt. So sometimes for the RTOS, it's really very important to secure such SRNs that are doesn't related to any or doesn't connect to any hardware source. So in this case, yeah, you could use this SRNs that could be highly dedicated to the RTOS, and this other SRNs will not generate any interrupt that comes out of the hardware. So at least from the operating system point of view, you know that this interrupt comes from software posted interrupts. All right, so I believe we have still 8 minutes. So let's continue. I have here this trap system. So for this trap system, what is basically the trap? So trap is occurrence or a result of certain events. So for example, if I access a certain memory and it's not allowed to, or I executed a certain instruction and for some reason something went not very well, or some non-maskable interrupt, for example. So all these are examples of the traps. And for the traps, they are defined into 8 classes. So the TriCore has this classification of 8 classes. You will find 8 classes of the traps. So these are here the 8 classes. So you'll find traps related to memory management unit, and traps related to internal protection or instruction error or context management error or system buses or ascension or system call, non-maskable traps. All these are different classes of different traps, and inside any of these classes you will find lots of traps, and in order to distinguish between the traps, you will use this TIN or trap identification number. So this will define the trap, the type of the trap inside any of these classes. So this is here how it works. All right, so here a quick overview about the different classes of the traps. So you'll find here class 0 till class 7, and these are the different traps per class. I will not go through all of this because of the time. And again, how could you form the trap vector table? So this is again the if you remember this for the interrupts, it was called base interrupt vector. Here it's called base trap vector. So this is the register that I will use in order to jump to the trap vector table, and I will or this trap number with the 3 bits of the BTV register, and then I will end up with a certain address inside this trap vector table. Again, notice that this is 0 here, so it is the alignment for the trap vector table. It's based on evenly byte alignment. And again, this BTV you could change. You could write with this instruction, so you could change or you could have more than one trap vector table if you would like, using this mtcr instruction where it writes the BTV register. All right, so for trap categorization, you could have asynchronous traps, hardware traps, or software traps. What will happen when the trap happens? Again, it's a very bit similar like interrupts, but a bit different. So you will end up with this trap vector will be accessed in order to fetch the first instruction of the trap handler. But before this happen, you will have again some of the stuff that needs to be done. So you will have the upper context will be saved, the A11 register will be updated, the trap identification number, it will be loaded in this data register, the stack pointer, it will be saved inside is set to the interrupt stack pointer. Again, input output mode is set to a supervisor mode. Protection register is set to 0. Call depth counter is cleared and and the limit here is 64. And permissions again to the global registers will be 0. It will not be disabled, so you cannot write to such a global registers. Interrupt system is globally disabled as well, and then the trap vector will be accessed. All right, so let's see here the protection memory. So for the TriCore, it definitely works with the safety critical embedded applications. So this is the value provided as well from the TriCore architecture. And you will find here it offers different schemes of the protection system. So the trap system, this is what we already saw. It offers as well the different privileges for different modes. So you will have, as we saw, user 0 mode, user 1 mode, and the supervisor mode. You could select whatever of these modes based on the access power that you need to assign for every task. And the third option for the memory protection here is the memory protection system. So the memory protection system, basically give you a control over which tasks is allowed to access which region of the memory and what type of this access. Is it reading or writing? So for the memory protection, you will have two types of protection. So mechanisms. So range-based or beige-based. So range-based, it's used for small and low-cost applications because it doesn't really require virtual memory. But for the beige-based memory protection, it requires the existence of the memory protection memory management unit, and it works like assigning different permissions to different memory pages. All right, so here you have the physical address space, you have the virtual address space. As we agree, we have a 4 gigabyte of the address space, and you will end up with 16 segments. Every segment is 256 megabytes. And this address space, it is divided into a higher address space and lower address space. Lower address space from 0H to 7H, and for the higher space from 8H to FH. And any address, any virtual address, first it needs to be translated before fetching the data from the memory. So I cannot fetch the data using the virtual address. It depends on if I access the upper part of the address space or the lower part, different things will happen. So if I try to access the upper part, so there is a direct translation. So that means the virtual address translation will be skipped, and the virtual address will work as a physical address. And if I access the lower address space and the processor is worked in physical mode, so again I will use a virtual address as a physical address. But if I use or if I access the memory space, the lower address space, and the processor is working in virtual mode. So in this case, I will use some certain table to translate the VBN or virtual page number to a physical page number in order to fetch the data. So this is here summarize what I already explained. So this is a virtual address. This is a physical address. Either I could add based on some condition, I could access the memory again without translations, or I could use a TLB table in order to fetch the physical page number from the virtual page number, and then I will end up with this physical address. I can control the processor if it work on a visual mode, virtual mode, or physical mode using this V bit inside this register that's called MMU_con. So this is from where I have control over if the processor work on a virtual mode or not. All right, so we saw here a direct translation, and so the direct translation, it uses range-based protection mechanism, and for the page table translation that's used with association with memory management unit, I assign basically different rights for different pages. So execute enable, for example, or write enable, or read enable, and this is here the BTE bits that control the different rights. So 0 means disallow and 1 means allow. Okay, so hold on, guys. We have a couple of more slides, and then we are done. So for the from the cacheability point of view, if the contents that are referred with this virtual address will be cached or not, this is here the hierarchy with it you can control if the data or if the instructions will be cached or not. So again, if this is a direct translation or not. If yes, so for example here, direct translation means I am accessing the upper part of the address space or the lower part, and assuming that the visual mode is not enabled. So yes, then I will check this BMA. So this BMA stands for physical memory attributes. So if the BMA allowing caching or not. So if yes, so the content will be cached. If no, the content will not be cached. And if there is no direct translation, so if I use this BTE translation, so yeah, you could check this C bit inside this BTE register. And if this C bit is 1, so yes, I will could be cache, and then I will need to check this BMA if allowing caching or not. If yes, so it will allow caching. So this is here the flow from where you know if the data that or the instructions that are referred with this instruction virtual address will be cached or not. All right, so let's cover a quick new topic, which is the floating point unit. So the floating point unit, as I mentioned earlier, it's an optional point, a component. So it could be existed, it could not be existed. It depends on whatever device you use. And the floating point unit, it is IEEE 754 compatible. And from the functional overview point, let's see what is this if you could offer. So it offer add and subtract, multiply and accumulate and divide instructions for your operands that comes to the floating point unit. It offers as well conversion from IEEE 754 single precisions to and from TriCore signed and unsigned integers and the 32-bit signed fractions as well. And you will find as well this qseed.f instruction that's most probably helpful in this calculations for the square root operation. And you could make a comparison between floating point numbers if you could like, and all the rounding modes that are available in the IEEE 754. There are 4 modes, so they are already implemented. And yeah, so you will find as well traps will be generated on some selected IEEE 754 exceptions. What the floating point unit cannot offer is yeah, or the shortage inside this FPU. So it only offers this single precision format. So double precision is not supported in this case. The denormalized numbers, they are not supported for the arithmetic operations. And the compliant to the reminder function, it's not implementing using this FPU because the effect of the multiple rounding when using the sequence of individually rounded instructions, they are different. And the fused multiply and accumulate operation, they are not part, which is what the floating point unit use, they are not part of IEEE 754 standard, and they could lead to a different results. And yeah, definitely, yeah, full compliance to the standard IEEE 754, not because the FPU doesn't offer this denormalized numbers. And again, if there is no FPU already existed on the hardware, and FPU instruction will cause a trap that needs to be handled. So this is here what the floating point unit could do, and this is here what are the shortages or the disadvantages when you use the floating point unit. All right, so last slide. This is here a kind of checklist that you need to check from the hardware point of view. So first you have to check the CPU clock. So you have to check the frequency. So basically the free running mode, it's around 17 megahertz. And if you want to use the instruction cache or if you want to use the data cache, so please make sure that it is usable by your system. So please verify that the instruction cache it's usable, because bypass is disabled. And it is the same case for the data cache as well. So verify that as the data cache is disabled, so that means bypass is disabled. And for BMU flashes, so BMU 0 flash and BMU 1 flash, you have to check the wait state because definitely the processor is faster than this memory. So you have to check that the default values for this will be, for the program flash, it's 8 wait states, and for the data flash, it's 15 wait state. And if you want to get some performance numbers out of the hardware using these performance counters that already existed on the hardware, so first you have to enable them. So by default, you are disabled. So at least this is a kind of checklist that you need to check before starting developing on the TriCore as well. I believe this is it for today. So this is here what we covered. Section 1, the TriCore architecture. Sorry guys if I speak a bit quickly, but yeah, as you already saw, the content, it was really very rich and very deep technical. Yeah, so maybe now we could see the